Hello and welcome to this discussion of extended surfaces. Now, the point of an extended surface is to attach a fin or some other structure to a wall. And the idea is we increase the heat transfer area for convection or radiation to increase the total heat transfer rate. Now, it's important to note here that if we look at the behavior of conduction and convection in a fin like this one, conduction is in this x direction, while convection is in the y direction, or sometimes the y and z direction, depending on the geometry of your fin. So it's important to note here that convection occurs in one direction and conduction in another. Now, we still usually assume 1D heat transfer in a fin like this. It is actually 2D, as we can see. However, the gradients in the y and the z directions are usually very small compared to those in the x direction. Now, this sounds a lot like lump capacitance, and in fact, the Biot number helps us determine the validity of this assumption. And then the basic result of this is that we add area available for heat transfer. We extend the wall to boost heat transfer from the surface. Now, it's important to note here that you want your material to have a very high thermal conductivity for this. The reason is high thermal conductivity means more heat transfer. It also helps to make this 1D approximation much more accurate. So the next question we have to ask ourselves is just how much a fin like this will improve the heat transfer from an object. So we start with the first law, and we look at this tiny differential control volume, which is just a slice of the pin fin, and we have heat in by conduction and heat out by conduction, and then we have heat out by convection, and we simply add these all up. And when we do, we get an equation that looks like this fin equation. Now, we have still assumed that we have 1D conditions, so we assume the temperature over the entire differential slice is a constant value. We also assume steady state, and we assume that the properties are constant. So we start by looking at what we call a constant area fin, a plane fin or a pin fin, where the cross-sectional area doesn't change with x. And if we do that, we can actually eliminate this area change term, or the second term in this equation. It also means that the perimeter in the third term is a constant. So since the heat equation can then be reduced, we start by defining the excess temperature. We have this theta value, which is temperature minus T infinity. It's just the temperature difference between the fin at position x and the fluid that's flowing over the fin. We also define this value m. So all this does is allow us to shorten the equation and make it simpler to write. And if you look, this is a function only of the material the fin is made out of, its perimeter, cross-sectional area, and then the heat transfer coefficient. So once we have this definition, then we can simplify the equation, and it looks just something like this. And we actually have seen this equation many times before. So we can very easily look and see that the solution has the form shown here. So we have e to the positive mx and e to the negative mx as two different parts of our solution. But we don't know C1 and C2 yet. And to find those values, we need to look at the boundary conditions. So our first boundary condition is just the base temperature. So that gives us one equation. Then we need to define the second boundary condition, and there's four possible cases. Convection from the tip of the fin, adiabatic tip, which means no heat transfer. We can say that the end of the fin has a constant temperature, or we can say the fin is infinitely long. So we're going to start with convection. That gives us convection heat transfer equals conduction heat transfer at the end of the fin, and allows us to write a second equation that relates C1 and C2. So now we have two equations, one from our base temperature and one from our boundary condition, and we can solve those two equations to come up with a solution like this. So the e to the positive and the e to the negative terms end up resulting in hyperbolic cosine and hyperbolic sines in our solution. Now there's another simplification, which is the infinite fin. For an infinite fin, theta equals 0 at x equals infinity. So that means that the value of C1 here has to be 0, because e to the infinity is going to be infinity. So if C1 is anything other than 0, we can't satisfy that infinite fin boundary condition. So that actually allows us to very simplify this equation. Now it's valid for this quantity ml is greater than 2.65. So we have to go back to m, which is the square root of hp over ka, multiply that by the length of the fin to see if we can use this approximation. So the next question is, how can we find the heat rate from the fin? It's easy. Once we've discovered the temperature distribution, T is a function of x, we can just use the conduction equation at the base of the fin. And so we have these tabulated solutions for that, where we have different boundary conditions, different temperature distributions, and different fin heat transfer rates. And it's important to note that we have some abbreviations here, capital M and lowercase m, that are defined down here in the bottom of this table. Now, in general, we don't use this type of method. We use the fin effectiveness to describe the heat transfer from the fin. So we look at the fin heat transfer over the heat transfer if the fin didn't exist. So we look at the actual heat transfer from a fin like this over the heat transfer if we had just had this tiny little area at the bottom. So that gives us total heat transfer over initial heat transfer. So the effectiveness describes the total increase in heat transfer. Now it must always be greater than 1 if you have a fin. And we want it to be as high as possible, but for a fin to be economical, it should be at least greater than 2. We can also look at the fin resistance. We can look at the resistance of the fin, which is just temperature difference divided by heat rate, and we can look at the resistance of just the base, which is 1 over HA, and we can define the effectiveness as the ratio of those resistances. So it's just another way of finding fin effectiveness. We also sometimes use the fin efficiency. The fin efficiency is based on the total area, which is the heat transfer if K was infinity, if there was perfect conduction in this material. So it's the fin heat transfer over the heat transfer in a perfect fin, which is why it's an efficiency rather than an effectiveness. So again, it's based on the total area, including the fin and so on. It actually is a maximum for no fin when L equals 0, because at that point your fin would be a perfect fin. The whole fin temperature would be the same as the base temperature. And it's a minimum when the fin is infinitely long. Now you'll note that effectiveness is just the opposite. It's a minimum for no fin and a maximum for an infinite fin. So there is a relationship between these two. Now we can also often find the fin efficiencies as tabulated or graphical forms. Here we have a graph which shows fin efficiency for different shapes as a function of this geometric parameter. So the fin effectiveness measures the increase in the heat transfer, whereas the fin efficiency is kind of a measure of the cost to benefit behavior. It's important to note that these are not the only factors, efficiency and effectiveness. Manufacturing costs are also important. So if you look at this graph, this parabolic fin has a higher effectiveness out here, however, or higher efficiency, but they're very expensive to manufacture because there's very precise machining that's required. The triangular fin is almost as good. In fact, in some cases it's better, but they're much, much more expensive, and so it may be a better option for your application. Let's also note that the only real difference here is the area involved. The fin efficiency is based on the fin area, and the fin effectiveness is based on the base area. So we can actually relate the fin effectiveness to the fin efficiency by looking at the ratio of those two areas. Finally, we should look at fin arrays. So if you have many fins on a surface, which is usually the case for a fin surface, we have to go beyond just the fin efficiency and fin effectiveness because they only characterize a single fin. So what we do is we use the surface efficiency. We can also then find the surface resistance. So the surface efficiency, if you look, is based on the fin area and the total area. So the total area here is the area of the fins plus the area of the base. So it represents the total area of this object, whereas area fin is just the area of a single fin. So we use this equation based on the fin efficiency to find the surface efficiency, and from the surface efficiency we can find the heat transfer rate. So step 1 is to find the fin efficiency from a table or a graph or a chart. And step 2 is to find the fin area and the total area. Step 3 is to use those three values to calculate surface efficiency. And then step 4 is to use the surface efficiency to calculate the total heat transfer rate.